All right, so the first stage of urine formation is glomerular filtration, and of course that is followed by tubular reabsorption, where about 99% of the filtrate re-enters the blood. And then the third stage is tubular secretion, where some substances will be selectively re-entering the filtrate. So today we're actually going to kind of work backwards. We're going to start with the glomerular filtration, and we're going to think about how that works. So let's just reiterate here then what the glomerulus itself actually is. This is a really nice scanning electron micrograph of glomeruli, and it's just a tuft of capillaries, and the glomerular capsule is actually removed from this picture. So the tuft of capillaries here is exposed. You can see it. We have an afferent arteriole here, an efferent arteriole here, so you can see that those nice rigid structures are entering and leaving the glomerular capillaries. So when we talk about the afferent and efferent arteriole, of course it is significant that they are both muscular and they both have a lot of pressure inside of them, and we can manipulate that, which we'll talk about in just a moment. The afferent arteriole is slightly larger than the efferent arteriole. One of the reasons for that is that the efferent arteriole is a stopper to make sure that the substances inside of the glomerulus are pushed into the glomerular capsule rather than just re-entering the blood automatically. And another reason is that because there is filtrate leaving out of the glomerulus and entering into the renal tubule system, there just isn't as much fluid leaving the glomerulus itself. When we take a look at the walls of the glomerulus, these bear some looking at. The first layer of the walls is called the endothelium. The endothelium is made of fenestrated capillaries. And of course the endothelium is just simple squamous epithelium, the same as any other endothelium that is present in a capillary bed. But the particular type of capillary in this case is the fenestrated capillaries. And so there are these fenestrations, or these fenestri, and these pores that are about 70 nanometers in diameter. Albumin is actually 35 nanometers in diameter. I'm correcting myself because in class I said micrometers, but it's actually nanometers. I can't believe I made that mistake. So the fenestrations are 70 nanometers in diameter, and albumin, which is a protein inside of the blood, it's the most by quantity it is the most numerous protein inside of the blood, is about 35 nanometers in diameter. And so at this point, what we would say is that albumin, or any protein in the blood, is actually able to leave through these fenestrations. So technically, all blood components other than cells are actually able to pass through the fenestrations because they are relatively large. But there are two other walls. For one thing, there is a basement membrane. The basement membrane surrounds the entirety of this endothelium. It's a gel-like glycoprotein layer. It has a negative charge to it. And since it is negatively charged, it actually repels proteins, which are generally anionic or negatively charged. And so that layer of glycoproteins tends to repel proteins and keep them in the blood. This is important. We want to make sure that proteins remain inside of the blood. When we talk about things being pushed or pressed out of the glomerulus, we can press out all kinds of things and reabsorb them, but proteins are tricky. When you push proteins out into the filtrate, then they're very difficult to reabsorb, and they oftentimes will be lost in the urine. So the third layer, the outermost layer, are called podocytes. Podocytes have these foot processes. So you can see these kind of weird-looking web-like structures. They surround the entirety of the endothelium there, and they have these filtration slits in between. These slit diaphragms will allow for structures that are only about 10 to 20 nanometers in diameter through. Remember that albumin is about 35 nanometers in diameter, so these slit diaphragms won't let albumin or any other protein through. So if they weren't already repelled by the glycoprotein layer, they will not slip through the foot processes of the podocytes. The tricky part, though, is that when we talk about kidney damage, oftentimes we're talking, generalized about kidney damage and what goes wrong with the kidneys. Well, there's several things that can go wrong, but this is one of the things that can go wrong as far as the original glomerular filtration in the first place. The foot processes themselves can actually start to break down, especially in situations where you have high blood pressure in the blood. That can be mitigated to a certain extent in the kidneys, but high blood pressure systemically is eventually going to start to affect the glomeruli themselves. And if you have high blood pressure pushing on these foot processes over a long period of time, it could actually start to break them down. And all of a sudden you have separations of these slits, and you have structures leaving the blood that shouldn't be. For example, proteins. If you have proteinuria, or proteins present in your urine, there's a possibility that it could be traced back to damaged podocytes. All right, let's talk about what the filtrate actually is. So filtrate is, well, we've called it future urine. Pardon me. But filtrate is actually the fluid that is pressed out of the glomerulus. Another way to define filtrate, it is basically the equivalent of blood plasma, except filtrate should not have the proteins. Remember that when you look at blood plasma, one of the big components of blood plasma is actually proteins, such as albumin. But in the filtrate, you should have taken care of with the podocytes and the glycoprotein basement membrane. You should have made sure ensured that all that stuff stayed in the blood and did not enter into the filtrate. So filtrate is basically the equivalent of blood plasma without any kind of protein. So what's found in blood plasma? Well, there's water. Water will be selectively reabsorbed in the second stage of urine formation during the tubular reabsorption stage. Just depending on whether you are dehydrated and need to retain water, or whether you've just recently drunk a lot of water and you need to get rid of water. So water is selectively reabsorbed. Ions, electrolytes, salts. These structures will also be selectively reabsorbed. One example of that, of course, is sodium. That's a biggie here. But another example of ions that are selectively reabsorbed is calcium. Remember that parathyroid hormone, the PTH, has a number of different ways of reabsorbing calcium back into the body. And one of the ways that it does it is it actually signals to the kidneys to reabsorb calcium. So ions, salts, electrolytes will be selectively resorbed depending on the needs of the body. Another component of the filtrate is glucose. Another component is amino acids. Glucose and amino acids are always resorbed into the body, unless you have a condition where your blood sugar levels are so high that you literally cannot retain any more glucose. There's such a thing as a transport maximum that does not allow you to go over a certain amount of reabsorption of glucose. So once you do have a certain amount of glucose that's been output into your filtrate, after that point you simply cannot resorb it, even though your body really loves glucose. Certain excessive amounts will remain inside of the filtrate. And it's one of the ways that we know that a person has diabetes mellitus. Okay, another component of your filtrate is nitrogenous wastes, the acid wastes of metabolism. These things are always going to be released. They will never be resorbed back into the body. They contribute to the acid content of the body, and they are also considered toxic. This is actually one of the very few places where you can actually get rid of these waste products, is in the kidneys. We get rid of some of them through sweat, through perspiration, but most of them will be through the kidneys. And then anything smaller than 3 nanometers is also going to be present in the filtrate. But those are the big components: water, ions, glucose, amino acids, and nitrogenous wastes. All right. If we look inside of a glomerulus, of course we have our afferent arteriole and our efferent arteriole. It behooves us to talk for a moment about the significance of these arterioles in some detail, because what we're going to be talking about next it's important to talk about it. So the afferent and efferent arteriole are both very muscular structures, as arterioles are. They have a muscular layer in there that allows us to either vasoconstrict or vasodilate them. Now, let's talk about the afferent arteriole. When we're talking about the afferent arteriole, of course, we're talking about bringing blood into the glomerulus. And if we want to vasodilate the afferent arteriole, what it's going to do is it's going to allow for an increased blood flow into the glomerulus. If we want to vasoconstrict the afferent arteriole, it decreases the blood flow into the glomerulus. Here's our efferent arteriole. So the afferent arteriole is all about blood flow into the glomerulus, which later we're going to talk about it as renal plasma flow, or one component of renal plasma flow. Okay, as far as the efferent arteriole doesn't have as much to do with the amount of fluids coming into the glomerulus as just maintaining a pressure inside of the glomerulus. Basically, if you vasoconstrict the efferent arterioles, it kind of causes the fluids to back up inside of the glomerulus, and that means that even more fluids are going to be pushed out. If you vasodilate the afferent arteriole, it allows more fluids out, and that decreases the fluids leaving the glomerulus. And that is going to be defined as the hydrostatic pressure inside of the glomerular capillary. Okay, so let's talk net filtration pressure, which we're looking at in this picture here. Net filtration pressure is basically where you have, as its name suggests, it's the net pressure of the filtrate leaving the glomerulus. As you can see, there are three main pressures that contribute to it. There's one outward pressure, which is the hydrostatic pressure of the glomerular capillary. And then there are two pressures going back inward. There is the osmotic pressure of the glomerular capillary. The osmotic pressure, as the name suggests, has to do with osmosis, or the flow of water back in. This is heavily dependent on the fact that there are a lot of proteins in the blood. The proteins that are still present in the blood here will allow for more water to be pushing backwards in. So remember, osmosis is the flow of water in the direction of a high concentration of something. So that high concentration of proteins that is retained inside of the glomerulus actually causes this osmotic pressure gradient here. And then we have another pressure, which is the hydrostatic pressure of the capillaries, of the capsule space, or the capsular space. And so there's just a small amount of pressure that's always going to be pushing back inward, because there is still a certain amount of fluid inside of the glomerular capsule itself. Okay, so the net filtration pressure, as we have shown here, is the outward pressures minus the inward pressures. So we have the outward hydrostatic pressure of the glomerular capillary. We're going to subtract the hydrostatic pressure of the capsular space plus the osmotic pressure of the glomerular capillary. So it's 55 millimeters of mercury minus 15 plus 30. So our net is going to be 10 millimeters of mercury. Now, who cares, right? Well, it turns out that the net filtration contributes heavily to the glomerular filtration rate. So let's talk about the glomerular filtration rate. I don't know which picture to land on here. Let's do this one. So who cares about net filtration pressure? It contributes to your glomerular filtration rate. So 180 liters per day of filtrate leaves out of the glomerulus. Let's go back to this picture here. 180 liters of fluid per day is going to leave out of your glomerulus. That comes down to a glomerular filtration rate, or a GFR, of 125 milliliters per minute. So the way that we calculate your GFR, and it's actually very important that the GFR remains just about where it is. So there's a couple of different mechanisms that we have that allow us to balance different things. Our 125 milliliters per minute is calculated by multiplying renal plasma flow by filtration fraction. So renal plasma flow is the amount of blood entering into the glomerulus in the first place. This, by the way, just a reminder, is contingent on the afferent arteriole and on cardiac output. And then there's the filtration fraction, which is the amount of filtrate actually leaving out of the glomerulus of the stuff that entered in the first place. And this is a function of the efferent arteriole. So, if we want to play around with our glomerular filtration rate a little bit, there's two different things we can do. We can either change the renal plasma flow, or we can change the filtration fraction. So, if, for example, we want to increase our GFR, our glomerular filtration rate, the first thing we might want to do is we might want to increase the renal plasma flow. And there's two ways to do this. You can either vasodilate the afferent arteriole, or you want to increase your cardiac output going all the way back to the heart. Remember that 20 to 25% of your cardiac output at rest is going to pass directly on through to the kidneys. And I forgot what I was going to say. So 20 to 25% passes through to the kidney. So if you increase your cardiac output, you are also increasing the amount that reaches the kidney. And secondly, after increasing your renal plasma flow, you can also increase your filtration fraction. And of the mechanisms we've discussed, there's only one that actually increases this, and that's to change your efferent arterioles. If you want to increase your filtration fraction, what you want to do is you want to vasoconstrict the efferent arterioles in order to push back and really push out and increase your glomerular pressure rates so that you have that much more flow leaving the glomerulus.